Crowhill here. Today we review a blonde ale and discuss relativity. Hello and welcome to Beer and Conversation with Pigweed and Crowhill. Good evening, Pigweed.
Good evening, Crowhill.
Hey, and look at Longinus.
Well, there's Longinus. What do you know?
So, what's on your mind this evening?
Well, I was driving down the road yesterday going to the beer store, believe it or not, and this fly had gotten trapped in the car.
Yeah.
And I had the air conditioning on because it was 95 degrees. And I said, all right, let me get this sucker out of here. I rolled the window down, and he wouldn't leave, and he wouldn't get sucked out. And I thought to myself, what if that guy even knows he's traveling at 60 miles an hour right now?
Well, from his frame of reference, maybe he's not.
From his frame of reference, he's not. But relative to somebody standing, to the construction guy on the side of the road, both he would be surprised to find out that he was flying at 60 miles an hour.
Well, that would actually maybe a point of pride to go home and say, I was going 65 miles an hour today.
How in the world are you doing that, Mr. Fly?
That's right, yeah.
Relativity.
All right, so what are we drinking here? Leffe, and somehow this looks a little small to me.
Yes, what do you know? You know what? That says more about you than it does about that bottle.
Well, maybe.
It says that you've held a lot of 12-ounce bottles in your day.
I think that I have. This is 11.2 ounces because it's from Europe, and they're crazy. And so this is a Belgian ale, an Abbey ale. It's a Belgian blonde. 6.6% alcohol.
Okay.
And I was surprised that you chose this.
Is this a new brewery, or has this one been around for a while?
Well, I mean, it was shortly after I was born in 1240 AD. That's right. Yeah. So this is an old one, but I was surprised that you would get a Belgian because you're not really a big fan of Belgians.
You know, it's like oysters. Every couple of years, I'll eat a raw oyster just to see if my palate's changed, and then I say, nope,
it's not.
Yeah. That's gross.
I love oysters,
and the same. And there are different degrees of that Belgian yeastiness.
Yes,
and sometimes it's just a hint, and it's fine, and sometimes it's just too much.
And the Belgian yeastiness is somewhat analogous, in my mind, to the Hefeweizen yeastiness.
Yes.
It's similar. But sometimes the Belgian yeastiness has a stronger, more assertive flavor to it.
Yeah, it's clovey.
Yeah, and you can smell it very clearly.
It's there. It's right there. It's clovey, and this one also says it has some vanilla notes. So let me know if you think you get some cloviness and some vanilla-ness.
Yeah, I do get a little cloviness. I do get that Belgian yeast flavor, which I can't describe as anything but the Belgian yeast flavor.
Yeah.
And maybe a touch of something like vanilla, but I find this to be very, very light in terms of how Belgian-y it is. It's not overpowering.
In all, I shy away from this Belgian-y flavor, but I try them and wondering if they, to the degree to which it's Belgian-y.
Yeah.
And the lower ones are fine, and the
but this is actually.
Say?
This is actually very nice. It has that clear Belgian flavor to it, but it also has a nice malty backbone to it.
Right.
And it's very drinkable.
This seems to be stretching things a little bit. This said best drunk before September of 2025.
Huh.
Well, this doesn't seem like a beer I would want to sit on my shelf for a year. But maybe not.
Well, it's 6.6, so maybe it'll survive
6.6, and it's not hop forward, so maybe.
Yeah, maybe. Well, I don't know.
They've been doing it since the 13th century, so I'm going to say that they know a little bit about beer.
They know a little bit about beer. If you want to get a good representative sample of that Belgian-y yeast flavor, this would be a good introduction.
Yeah.
To go out and get one of these guys.
It was $10.99.
Yeah, it's not terribly expensive.
Perfectly reasonable.
Yeah. Well, they probably haven't had to pay rent for a while. They probably paid it off in like 1340.
Right, and because it's and they still have some monks around, so that and they call it a monastery.
Yeah.
So that they get tax breaks.
Probably. Yeah.
So we can't get to relativity without talking about a certain young man from Germany.
Yeah.
Born in 1879.
Albert Einstein, one of the things that I love about Albert Einstein is he was a patent clerk. He wasn't like some, university-trained egghead guy. He was some guy working in the patent office.
Well, I thought, I'm going to upgrade patent clerk a little bit because I thought he's just like working at essentially the post office.
No. Yeah.
But he's reviewing intellectual property patents.
Yes. One of the Crowhill clan does that, actually.
Okay.
That's his job. And so there is some intellectual rigor to that sort of thing.
Yes.
Oh, yeah.
But it also isn't so rigorous that you can't sit around and do thought experiments.
Yes, and his thought experiments, exactly. And I really wanted to find, and I couldn't find it. Carl Sagan, a long time ago, did this great show where he illustrated the kinds of thought experiments that Albert Einstein did to come up with his relative. And he would have two people riding bikes down this trail. I can picture it in my mind, the way Carl Sagan explained it, and how Einstein came up with some of his theories about, two people are moving and they have different frames of reference, and how do you relate those two frames of reference together, and why? Because one of the things that Einstein came up with was the idea that the speed of light has to be constant from every frame of reference.
Yeah.
And he came up with that idea from some of his thought experiments about imagining things moving in different ways.
Yeah, that's nuts. So, we talked about last show about those things that everybody knows, which are false.
Yes.
It's that there was a national campaign, I guess, to inspire mediocre students that said when it came to education, Einstein was no Einstein.
Yeah.
And we all know that Einstein failed math. All right, that's just not true. He was an excellent student. When he took the test to get into the university, you had it's 1 through 5 scale, and you're supposed to. He did poorly in French. And by poorly, I mean a 3 out of 5 instead of a 5 out of 5. Yeah. And and then he got all 3 in chemistry or something like that. And so that eventually led to this false notion that he was a bad student and he failed math. Okay,
I think a lot of that stuff is. So when you're talking to the failed student, who's a dummy, they're just stupid and they don't really know what's going on. Einstein was dumb too.
Yeah,
right.
Right. He didn't speak as a child. Well, I mean, by the time he was in preschool, he was caught up to everybody else. Yeah. Maybe at 2, when other kids were already speaking, he was kind of a slow. Yeah, all right. But So is it a beneficial lie, a helpful lie for what was the term for that? Like
a useful fiction.
Yeah, a useful fiction is to tell mediocre students that, hey, just because you're not doing that great in school right now doesn't mean you can't have a great effect on the world. Or is it just running down to man Einstein? It ain't fair.
That's an interesting question.
I think you're right.
Because I think there's 2 ways to look at that.
Useful fiction.
There's one question is it a useful fiction to say that somebody, whether it's Einstein or not,
didn't show a lot of promise.
Didn't show a lot of promise and eventually turned into more than you expected.
That's pretty good.
I think
okay
that's
with
a good
that.
story. That's a good story.
Good, right.
Yeah. Now, whether it should be pinned on Einstein, that's another question.
I heard this comedian. He goes, "How come we only use Einstein's name when you're calling someone an idiot?" It's like, well, Einstein, where'd you park the car? It's almost like a criticism.
That's right. It's an underhanded. That's damning with faint praise.
Right.
He was an airhead, right? He was he lacked that. The myth is he lacked that common sense.
Which I can totally get that.
There are stories that he would walk into the closet because he was like, I'm going to go for a walk, and he'd walk into the closet.
Get lost because he's walking down the street thinking about abstract.
Because he's got all this stuff going on in his head.
Right now, and what was the state of theoretical physicists, I think of physics at the time as being very practical, right? It's
well, you had a lot of things going on at that time. You had there were a lot of people working on a lot of different areas of physics.
Right, so time-wise, he turned 21 in 1900. That's kind of an easy way to say this is where we are.
So he was 26 when he came out in 1905 with his groundbreaking papers.
Now I'm trying to remember. I'm trying to remember the name. I listened to a In Our Time episode on Einstein.
Yeah, and
I'm trying to remember the name of the physicist that Einstein said was one of his main.
I know Max Planck was a big name of the time.
Right.
But one of the ones that was one of Einstein's inspirations, I'm trying to remember who it was. I don't think it was Heisenberg.
What's interesting, I know where you're going. What I take from this is he wasn't a lone genius.
Right. There were a lot of geniuses. Yeah.
Right. Yeah. And so I find it maybe we'll do this at the end. Is why his enduring claim to being the most brilliant scientist ever, when really he was just he had colleagues and people that he admired and respected but somehow his face and his name rose above all of the rest to be the one name that just the dumbest person can say, "Hey, Einstein, where'd you park the car?" Right? Nobody says about Max Planck.
Right. Yeah. And he's also a genius.
Right. I think it goes into the fact too that we always want to, or if you go back to your perennial myth, the idea that it's the guy that's not so... The guy with the fresh ideas is the guy that is not solidly in the system.
Right. The outsider...
He was the patent clerk that came up with,
Came out of nowhere. But really, he was fully collaborative kind of a guy.
Right.
He totally worked with his peers. He wasn't the guy in the basement of the patent office all by himself with a chalkboard, who then sprung out. Science. That's not how science works.
There's always going to be some mythology.
But there's but there was just something about his image and the events of his life, and we'll get into that with the 5 papers that just isolate that made him. It was. Well, you want to do 1905?
Yeah. Sure, so that's the miracle year.
Right.
He came 4 papers on various things, and the most important one being special relativity. And so there's special relativity and there's general relativity.
Right. And so hold on, we got what was the first? The first. So Max Planck. So you had light.
Yes.
Theories of light. And Newton.
Yes.
As an electromagnetic wave, or as a wave.
Right. So what about ether?
Oh, okay. So one of the problems that early scientists had to deal with is how something travels through space if space is just nothing.
Yeah.
Right? So that they started to think of space as having this substance to it, which they called ether.
Right. And because sound needs something to pass through. It passes through water. It passes through. It doesn't pass through space.
Yes. That's right. Right.
So when light passes through space, it's like, well, what is going on? Where's the substance?
And not only that,
but was like a Newton problem too, right?
Exactly. Yes. So Newton came up with this idea of gravitation, where this massive object over here exerts some strange force on that massive object over there. Well, how the heck does that happen? Right. Like, what it came to be called spooky action at a distance. And the concept of there being some sort of a connection between those two things made a whole lot more sense, because how is it that this thing exists over here, and then there's all this nothing, and that thing exists over there, and these two things have some interaction, but that doesn't, it's kind of hard to understand. So ether was kind of an early sense of trying to understand how all this kind of stuff works.
But Einstein had a problem with ether.
Yeah.
And so So that was his first paper. The second paper was the existence of atoms. So
right, which
atomic theory eventually comes out of Einstein.
Right, which what he does is they have noticed, or they, meaning the scientists, have observed that very small pollen particles look like they're moving at random, and they should be moving in a certain way. And then Einstein was the one that said, well, they're moving. They're having small little different movements,
Brownian motion, and that kind of stuff.
Movements. Mm-hmm. And it's sort of like having a basketball flying through the air and being hit by tennis balls. And the tennis balls are the atoms, and the basketball is the pollen. So he was like, well, this sort of proves that there are atoms out there. And through various other sort of experiments, that's when they said, yeah, he kind of like helped us prove that atoms exist, which before that nobody really knew, because nobody's really seen an atom.
Right. Well, you have to think of the kinds of technology they had. Their ability.
What was their understanding of the smallest particle at the time?
And they just had optical microscopes and things. So it's not the most wonderful view of things.
And the other one was, his papers, was the idea that light is a photon, is a particle, and not a wave. And Max Planck thought it was a wave, and a lot of everybody else was leaning towards the wave. He said, no, it's a particle.
So on the electromagnetics of motion of moving bodies, that's when he said that gravity, that if light has mass, then it will be affected by gravity.
And it'll bend, right.
Right, and let me get to the fourth one before we get to this is still 1905. The fundamental relationship between mass and energy, and the E equals mc squared. So that was the fourth one. But this is all theoretical. Yes. And so he becomes a rock star in 1919 because you can't look at the sun. You can't see the light from a star being
bent around the sun.
Bent around the sun.
Yeah. So this to me is one of the huge mysteries of life, that somebody can just think about things mathematically and conceptually, and write equations down and work on the math and come up with this theory that turns out to actually be true.
And aren't there some of these things that have just been proven in the last 20 years?
Yes.
And it's got to be this way. Of course, we have no way of knowing. Some of
the things had to do with gravitational lenses, the idea of the way light bends around a star. Some of the things had to do with the orbit of Mercury. Some of the things had to do with black holes. Mm-hmm. So a lot of the things that were predicted by Einstein's special and general theories, yes, it's only recently they've been confirmed, but I'm just fascinated by this concept.
I know
that somebody can be imagining this stuff. I'm like, why would that be true? Right. Like the human brain was evolved to do certain things, right? Like find a mate, kill the elephant, repel the Hun. Those are the kind of things, and that somehow it's the human brain is equipped to do these amazing things, to figure out the nature of light. And
and for him to write these 4 papers with no way to actually test them,
right?
He's like, I'm okay with that because
I believe in the math.
yes, because then the math works.
Yes,
and so it has to be true.
And God doesn't play dice with the universe. And
exactly. And then 14 years later, we had the opportunity to check it out. And how did that go?
It was confirmed.
It was confirmed.
It was confirmed, and the way they
we said, you can't stare into the moon. Yeah. I mean, into the.
They had to go down into the southern hemisphere, and there was a solar eclipse at that time, and the idea was the light from some distant star was going to bend around the sun.
Right,
and
you had to be in the right spot. This was a British expedition. Yeah, you had to be in the right spot for the total eclipse, right. And I don't know how. I had no idea how.
Yeah.
But they were like, by golly,
he was right.
He's right. And so the star, relative to where you are, is not really where you think it is, because the light from that star is being affected by mass of objects in between, which bent the light to give. Am I saying? Is this making sense?
So I think the idea, if you imagine that light from a star goes out in every direction, right? But only some of it is coming to us so that we can see it. So some of the light from that star, you would think that it was a straight line from that star to us. But if there's a gravity well in between, it's going to bend the light. So conceivably what would happen is a star could be seen on both sides of the sun because it's bending around one side of the sun and it's bending around the other side of the sun. So that you would see it sort of two different ways.
Right.
And that, I think that's what they tested.
Okay.
And that proves the special theory of relativity, and that takes them to create general theory of relativity. But let's go back and talk about what special theory was
first. Isn't it funny that special was first and general was later? But anyway, yeah.
So special theory of relativity, which was the one that all of a sudden said.
This was a few years later, like 1912 or something, right? Or was this part of the?
No,
was it part of the four?
Special relativity was the first one, and then general relativity was later.
But was it part of the 1905 four pack?
Mm-hmm.
Right.
Go ahead.
So, special theory of relativity was the one that said, "Oh, wait a minute. The only absolute we have is the speed of light, and time is relative."
Yeah,
and time stops becoming absolute. So now, when we read the H.G. Wells Time Machine, of course, he was looking at that as being absolute, and all of a sudden, Einstein saying, "No, it's relative," and he starts to go through these thought experiments and sort of proves it, and then starts to, and later it gets proven by what you were saying about the GPS thing, which is fascinating.
So it's not your dimensions, right, in space plus time. It's a thing that is space-time.
Yeah. Yes.
Right.
But I think the way.
Can you help me out here?
So there are two fundamental assumptions in special relativity. The first one is that the laws of physics apply in every inertial frame of reference. In other words, if from my frame of reference, as long as I'm not accelerating, then I can apply the laws of physics in my frame of reference, and somebody else in some other position can. So if somebody is on a train that's going by at some ridiculous speed, and I'm standing on the platform, then the laws of physics apply to that guy going on the train just as well as they apply to me standing on the platform. So,
independently almost.
Well, yeah, like the laws of physics apply there and they apply here. So that was one of the assumptions of special relativity. The other one was that the speed of light is constant for every observer.
All right, so let me jump in. So it's Halloween night. I'm standing in the back of a pickup truck going 30 miles an hour.
Mm-hmm.
I throw an egg at a poor child at 30 miles an hour. It hits him at 60 miles an hour because I'm adding the two.
Yes.
Now, I'm in a spaceship flying, and I shoot a flashlight out the front. That light. You're telling me that light is not going the speed of light plus 1,000 miles an hour that I'm traveling.
Exactly.
Why is that? Why can't I add the two together like I did with the truck and the egg?
Right. So with everything that we observe in our normal life, Newtonian mechanics, where you would add those two together, works. Okay. In what Einstein realized was that doesn't work at high speeds. Now, exactly how he figured that out, I don't really know. But
just
if you're in a train,
math.
If you're in a train going half the speed of light, and you shine a flashlight, then from your frame of reference, the light is leaving your train at the speed of light.
180,000 miles.
186,000 miles.
What about a guy in another train going half the speed of light, watching you?
Yes, that's where it gets difficult. So you have somebody going by at half the speed of light, and you're standing on the platform, and what he realized was that if you start to do calculations from the perspectives of the two different people, the person on the train and the person on the platform, you started ending up with these weird problems. And that's where he realized that, remember, speed is distance over time, right? Yeah. Miles per hour or meters per second or whatever,
gotcha.
Right? So if you try to do various explanations of what's going on from the perspective of the guy sitting on the train that's going half the speed of light, you're going to come up with one way of looking at it. And if you do it from the perspective of the person standing on the platform, you're going to come up with another perspective, both of which are perfectly valid. But the only way to make them work is if the speed of light is constant in both positions, then time and distance must change.
Right. So, like, if you're going 179,000 miles per second,
right,
and you turn on your flashlight,
yes,
you would measure that light as going 180,000 miles per second, or not 1,000 miles per second.
186, but yeah.
186.
So yeah, so from your perspective, that's how fast it's going.
Right.
But somebody watching from a different frame of reference would have a different way of calculating it. And the way to reconcile all those things is to realize distance and time contraction. So that from, like, if I am standing on the platform and somebody's going by at half the speed of light, time is different for them than it is for me. And distance is different from them than it is for me.
And that's the only way to make the math work.
Exactly. So,
but is it at very high speeds? Like, does there exist a time measurement device that is going to recognize flying a plane at 400 miles an hour around the world? You know what I mean? Like, you fly all the way around the world and you land. Is your watch 1 second different, or nanoseconds to the point that they're immeasurable, and that this only really matters when you're talking about half the speed of light, mostly the speed of light?
That's a great question. So the first thing to realize is that everything depends on your frame of reference. So the frame of reference of the person standing on the planet, we like to think, here I am, I'm stable, I'm not moving.
In the center of the universe.
Yeah, but no, the Earth is turning, it's going around the sun's moving through the galaxy. All these
the whole
things
solar
are
system is moving.
Everything is moving all the time. So the question is from a particular frame of reference. But then, if, in terms of determining this time dilation stuff, if they have tested it with supersonic jets flying around the Earth, mm-hmm. where they're comparing the frame of reference, with an atomic clock, comparing the frame of reference of somebody on the Earth with the frame of reference of the plane flying around the Earth, and they've been able to say, yes, it does work, that the clock on the plane flying really fast goes slower than the clock on the Earth.
All right, so then we check off another theoretical, in Einstein's day, that has a practical, not necessarily usage, but an experimental verification.
Yes, and it's interesting you raise the word practical, because yes, it was experimentally verified, but it wasn't really practical until relatively recently.
Yeah, so would you need this to, did they use relativity, they're aware of relativity, obviously, to put a man on the moon? Or is that straight up good old...
I don't think
I think most of it was good old
Newtonian physics.
Yeah. They were using slide rules and stuff.
Exactly.
Like
you didn't really need to... Thanks, Bill.
Well, before you say that, let me just tell you what Brian Greenan says.
He's a good communicator.
And he's a good communicator, but he wrote, and this kind of blew me away, he says that everything is moving at the speed of light But physical objects are moving at the speed of light minus distance, minus going this way, minus the motion in the 3 dimensions. So we're moving at the speed of light, but we minus the 27,000 miles. We're spinning around. We're going through an orbit, right, on the Earth, and we're spinning 27,000 miles around this way. The Earth is expanding out in the universe, minus that thing. So we're all moving at the to make light absolute. That has to be the one thing that we are referencing in it. So we're all moving at the speed of light minus all the movement we're doing otherwise.
I haven't thought about it that way. So I got to think about that one. Yeah, so the interesting thing to me, I don't know, it's just words, but it's interesting to me that special relativity came out before general relativity.
All right, so one of them applies at very high speeds and very large objects, and then others are
with very small things.
Very small things at the atomic level,
and also with gravity. So special relativity, which came out first, had to do with the speed of light and every frame of reference being independent and that sort of thing. General relativity had more to do with gravity, and apparently there have been some elements of general relativity that have not been confirmed by modern physics, and there are some questions about how gravity actually works.
Well, yes. Well, that's the great thing is Newton decided, I don't know where it comes from,
but this is the equation.
This is how it works, and it works all the time. So there's something going on. Yeah. Why do masses suck? Because if you take a wet frisbee and spin it, everything flies outward.
Yeah.
Why would a spinning mass suck inward?
Yeah.
I don't know, and nobody knows. But damn it, I'm telling you, it's there. In the same way but which is why the idea of ether makes perfect sense. I don't know, but if for the math to work, in order for the math to work, we have to have this thing that's called dark matter, which is 90% of all the mass in the universe.
Yeah, that doesn't sit well with me. But we'll have to see how that works out. I hope they figure that out before I'm dead. But I remember when I was in high school studying physics and learning about the way gravity worked, I had a problem with the concept of the mass of a sphere. You could calculate gravity as if the entire mass of the sphere existed at the very center.
Right.
And I had some reasons why I thought that was wrong. So I showed it to my physics teacher, and he said, well, I understand what you're saying here, but you're wrong, but I can't tell you why you're wrong.
Because the math works.
Yeah. So I went to my dad, who was a NASA engineer, and I showed him my explanation of why I didn't think this was right. And he looked at it and said, I can't figure out what's wrong with what you said, but I can tell you this. When they send probes to Jupiter, they get there.
What's your argument
and this
now?
is the math that they use.
Right.
And it wasn't until I got to the University of Maryland that the Schlonsky Clinic guys, I went and I explained my problem to them. They said, oh, no, this is it. And they explained it to me quickly. Yeah, exactly. So I think one of the things about science is even when you don't understand exactly how or why, like with Newton, what you were saying about, I don't know why this object here affects, it still works.
Yeah, we don't, right? Because we don't know what gravity is.
Right.
But we know its relationship to mass.
Yes.
And we know that the math always works. So
yes.
we know it's there.
Yeah.
So like I was saying, you can put a man on the moon with Newtonian physics. So this relativistic stuff is what? To predict how solar systems, galaxies interact at vast spaces, and not really practical here on Earth. Until this article said 8 ways how that relativity is, applicable in our real lives.
Yeah.
This is the only one that I've thought really straight up applicable, and it's has to do with our GPS systems.
Right.
And you have to factor in the speed, because to me, the speed of a satellite is way too low to possibly, it's so far from the speed of light that it can't possibly be affected. And so, what do they call it? Geocentric?
Geosynchronous. Geosynchronous orbit is way out there.
But it's when it stays in the same spot relative to the Earth, right?
Yep.
How fast do you think that's going?
Relative to the Earth?
Yes.
It's, I'm not positive. I think it's like several hundreds of thousands of miles an hour.
But it's not. It's 22,000 miles away, and it's 7,000 miles an hour.
Only 7,000. That can't be right.
Or less, because it could be kilometers.
So
because the Earth is because if it's 26,000 miles around and it goes in 24 hours, then while standing here is 1,000 miles an hour.
Yes.
So if you're as you go out, of course, it gets more and more and more. So now you're at 7,000. At any rate, it's not 1,000,000 miles an hour.
Right, sure.
It's not somewhere where you think that relativity is going to play a part. But according to this article here, it says the effects of gravity. The time dilation effect goes about 7 microseconds, which is a millionth of a second. Who cares about that? The difference is very real. If no relativistic effects were accounted for, a GPS unit that tells you it's a half mile to the next gas station would be 5 miles off after only 1 day. Wow. Which I find that remarkable. Mm-hmm. That it's that applicable. I just thought it was still so theoretical and had to do with the motions of galaxies or traveling at near the speed of light. Mm-hmm. That's practical and real.
Yeah, it is very real. Yeah, one of the things that...
I still don't get how... it's within 10 feet. You're pulling up to a stop sign, and it's telling you...
I know. It's... how far do
and it's 22,000 miles away.
It's amazing how accurate it is. One of the things that has always bugged me about one of the explanations of curved space, which is part of the theory of general relativity, is the idea is if you were to imagine you had a trampoline...
Yeah, and curved space. Go ahead.
And you put a big weight in the middle of the trampoline, right? Then it would come down at that point, and it would all curve around.
There's a graph drawn on the trampoline, which looks nice and flat and square.
Yeah, and then you put a weight on it, and it's different because. And if you were to take a little marble and push it around there, if you were to do it just right, you could get that marble orbiting around that heavy weight that you put in the middle of it, because it would just be traveling along that line. I understand that perfectly well. Here's the thing that bugs me about it. That whole model of the weight on the curved thing assumes gravity. Right? The whole mental image, the whole model assumes that I'm in a place where there's gravity pulling this weight down, bending space, and making the marble move out. I want to hear a theoretical explanation of curved space that doesn't assume that perspective of gravity that I have. I don't know how that's possible or if it's possible. I want to hear that.
Well, the thing is that example is showing is an example of curved space, but it's only 2 dimensions into 3 dimensions.
Exactly. Yeah.
And then what we want to do is
it's just a helpful way for simpletons like us.
Exactly. It's a helpful way for us to understand it, and I get that. But I want to hear something like, what does it mean for space to be curved like that? It's hard to wrap your brain around it. I can picture that thing where you put You put something heavy on a trampoline and it blows. I get that. That's easy. But I want to understand what that means in the concept of 3 or 4 dimensional space time. That
time and space are not.
They're not fixed.
Right.
Yeah. And Newton would have believed that time was fixed everywhere in the universe. Right?
Why wouldn't you think that?
That the
clock, I'm still pretty dang
still
certain it is. You go about your life thinking that, of course.
Exactly. So Newton would have thought that time was like the same everywhere. There's this clock going on in the universe somewhere. Tick, 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 and that happens
distance
everywhere.
to get from here to there is what it is.
Yes. And so those two things, time and distance, both are not what we think they are.
That's right.
They're not fixed. They depend upon gravity and everything else. So it's pretty weird.
All right.
Well, that's the thing is, I mean, there is no good definition of time. I mean, the best definition of time is that which clocks measure. But we don't know what it is.
Right. And the relationship between things is what it is.
But
it's not a spatial relationship.
In time travel theory, if you were to say that time is something, time doesn't exist, that everything is happening all at once, except the only way for human beings to experience it is this linear view, then it's only our relativistic perspective of time, and you get
into all kinds of weird stuff.
Yes, and that just sounds like
sounds like a Star Trek episode.
Or you're just smoking weed in college at 3 a.m. Yeah. How about one practical thing?
Okay.
If his atomic theory was vital to the creation of the atomic bomb, why was he not a part of the Manhattan Project?
Yeah, that's interesting. And the movie...
Yeah, in the Oppenheimer
movie,
he was in the movie, but they didn't explain why he wasn't.
Well, there is one brief point where Oppenheimer basically says, he's 10 years behind. And if you think about it,
which is nuts. But of course, he's an elderly man at this point.
Yeah.
Right.
And
so
if you think
about it,
he
was 21 and 19 years old. So by 1945. Well, I mean, he's not elderly. Oh my gosh, he's not much older than I am. But anyway, he's in his 60s. But he's probably not at the cutting edge.
No, and the thing that's really amazing about, I've just rewatched Oppenheimer recently, and you think about the brain power in those rooms.
Jeez,
you have Oppenheimer up there at the chalkboard, and he's talking. He's got 25, 30 guys in there. Every one of them has got like 160 IQ or something.
Right, and most of them under 30, right?
Yes, and these guys are absolute geniuses, and they're all working on this project. It's just amazing to think about it.
It was amazing. All right,
the other thing, too, about Einstein is, I mean, he was a classical physicist right till the end, even though he sort of gave birth to quantum mechanics.
Right, that's a good point. He really was not an applied physicist. Yeah,
but he also didn't like a lot of the Heisenberg uncertainty principle. There are certain things about the way physics was going that he didn't like. He didn't like the idea. Well, there's his famous saying, "God doesn't play dice with the universe," and not that Einstein believed in God or anything. He was just used that as an expression. But the idea that things could be either this or that, like the famous Schrodinger's cat experiment and that kind of thing. That kind of thing just chaffed Einstein. He didn't like that. He didn't like this idea of things being indeterminate. And that seems to be a big component of quantum theory. And that's what's going on right now, is the conflict between quantum theory and general relativity in terms of explaining things like gravity.
All right, well, that was simple enough. I think.
I think the viewers are have it all figured out now.
Well, I mean, it's a little light topic for you.
A little light topic, yes. This is a light topic.
We consider this a light, oddly enough. Well, Longinus, thank you for your help.
Yes.
Cheers.
Thanks so much for listening to Beer and Conversation with Pigweed and Crowhill. Remember to visit us at pigweedandcrowhill.com or send us an email at pigweedshow@gmail.com.